10-year-old daughter that still just really loves the kitty and is always mauling the cat, and the cat will flip out every now and then. Go. All right, well, we better get going on the binomial theorem. We just started, right, last time? And we just had, that's on the board is not true. Let's see, 12.5, 6.2. This 12.5 is going to be due on Thursday. So we're going to finish the binomial theorem today. We're going to do, and then we're going to start trigonometry. Today we're moving into our trig, and it's to trig the rest of the way. So let's, the 12.5, this is the last topic other than trig in the course. So this binomial theorem. So I put it on the board last time, right? I did one example, and nobody remembers what I did, maybe. I mean, because we didn't have any homework on it, so I'm assuming you really haven't given it any thought. So kind of let me just take it over again kind of from scratch. And write out the way. What you do is you look at the power. So remember, we want a shortcut way. Because if I was to do this by hand, it would be a big pain, right? I could. I don't want to. It would be really painful. I could go 3x plus 1, 3x plus 1, 3x plus 1. Don't write this down. That's not really what I'm going to do. Well, maybe I will. Don't write it down, though. Because it's not really the way this. You get, what, 6x plus 1. These two would also make 9x squared. This one's small enough. I might be able to do it. Boom, boom, boom. So that'd be what? 81 x to the fourth. Well, I'm already tired. I don't want to go anymore. All right, anyway. So it'd be a big pain, right? You just foil, foil, foil. And that's only fourth power. We have a lot higher powers than that. So it's a big pain to do it. And so we have this shortcut formula for foiling a whole bunch of two-termed things. Binomial theorem, right? It's for two things. We have a 3x and a 1. So it's anytime you have parentheses, you have two things in there. Could be like a w to the fourth and a 7z to the third or whatever, to the fourth power or the seventh power or the 10th power. You know, two things to some big power. Let's jump right to the answer. That's what the binomial theorem is how to jump right to the answer for two things to a big power, because that's used a lot in higher math as you go up the line. So what's the formula? Well, you take the power, remember what it is, and you do like the 0 and 1, 2, 3, go all the way until the numbers match, 4, 4, right? So you start at 0, go all the way up the line. Remember what those are? I showed you how to do those on your calculator and from Pascal's triangle and by hand. I give you 3 ways to get those. But before I do that again, what do you do here? Then you put the first thing, the 3x, and the second thing, the 1. 3x1, 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 3x1. 3x1. You know, whatever the two things are in the binomial two-term theorem, right? You write those two things, and then you put the right powers on them. How do you know what the powers are? Where do you start? With whatever power you got on the thing. If I was a 10th power, I'd start at 10. Then you just go down the line. 4, 3, 2, 1, 0. And then vice versa. You start with 0. 1, 2, 3, 4. Good? So there's basically, now we just got to figure that stuff out, but that is the pattern of the binomial theorem. Are we good with that so far? Now, let's figure out, how do we figure out the, the 4, 0, 4, 1, all that kind of stuff? Well, again, I gave you 3 ways. Any of those ways are fine with me. I don't care at all. Calculator first off. So, like you could do, like, say, 4, 2 on your calculator. It's 4C2 on your calculator. Remember, that's under the math, but if you have the TIs, it's under the math button. You got to hit, like, math. Then you got to go to the right a couple times to PRB, or 3 times, I think it is, to the PRB, probability, and then go down, and you'll see the C. So you got to do 4C2. You'll get, is it 6? Yeah, I think it's 6. Yeah, 6. So, and we'll be able to get that 4 choose 2. It's called choose. It's a probability thing. 4 choose 2 comes out 6, right? Okay, now that's by calculator, and that's totally fine. This will be on the graphing calculator part on the test next week. Next test is next Thursday, right? Did I say that already? Maybe I didn't say that. Next Thursday. Exam number 4? Exam number 4 next Thursday. So a week and 2 days from now, 9 days from now. Next Thursday, May, whatever that is. Next Thursday is May 4th. Will be exam number 4. Our last last one other than the final. So anyway, and so these binomial will be on the part where you can use your graphing calculator. So you can just use the C button to get it if you want, or I'll also show you by hand if you want. By hand is you start with the first number, 4, and you do, this is where you start, and this is 2 numbers. So 4 times 3 over the second number all the way down to 1, which wasn't far, 2 times 1. That's the by hand. You start at 4, do 2 numbers, you know. So say it was 10, 4 or something. Then I would start at 10, 9, 8, 7, do 4 numbers over 4 all the way down. Does that make sense? That's the by hand way. You start at 10, do 4 numbers on the top, right? Start at 10, do 4 numbers, and then the bottom is the 4 all the way down to 1. So there's by hand. If you want to do it by hand, that's what those things mean. If you want to do it by calculator, you can use the C button on your calculator. Okay. And then the last way is I gave you Pascal's triangle. Remember that? I said, well, you can just do Pascal's. That's where you put the ones in the big old triangle thing. And then you add them up. So this would be 1 and 1 makes 2. Remember, 1 plus 1 makes 2. 1 and 2 makes 3. 1 and 2 makes 3. And then you put always 1s on the outside. 1 and 3 makes 4. 3 and 3 makes 6. 3 and 1 makes 4. Right? And well, how do you know where they are? Well, let me get this out of the way. Where you find them on Pascal's triangle is basically if you're looking for 4, this is the it starts right there at the 1, 1. This is first power, second power, third power, fourth. So this is it. 1, 4, 6, 4, 1. That means these coefficients, this will be 1, this will be 4, this will be 6, this will be 4, this will be 1. Because I have a 4th power. So Pascal's triangle. Everybody see how I'm doing Pascal's triangle there? That old famous philosopher, mathematician, astronomer. And they did everything back in the day. 1700s. They would do math and astronomy and science and philosophy. They would do it all. Now we're so specialized. There's a lot more knowledge out there. There's a lot more to know. So we have, doctors of just the left pinky finger. They're real specialized. Excuse me. Anyway, Pascal did a lot of stuff, and he did some math, and that's his little triangle thing he came up with. Are we okay with that, with getting those coefficients? Whichever way you want, by calculator, by hand, or by Pascal's triangle. Okay, so now let's do the rest of the stuff. So 3x to the 4th. That's the whole 3x to the 4th power. So that's going to be 3 to the 4th power, which is 81. X to the 4th. And 1 to the 0 power is just 1. Good so far? The next one is 3x to the 3rd. What's that? 27. X to the 3rd times 1. The next one is 9x squared times 1. And then 3x times 1 and 1. Right? Because anything to the 0 power is 1. Right? All right, put it all together. What do we got? This is 81 x to 1. Am I on the screen? Yeah. This is 4 times 27. What's that? 80. 108. Thank you. 108 x cubed. 54x squared. 12x and 1. Those are the terms, the answers. There's the answer. Add those up. That's the answer. Those are the terms of the answer to foiling that thing 4 times. Are we good on that? Questions I can answer on that one? So that's the binomial theorem. All right, let's try another one. Okay, so give that one a try. Give me a second. Start doing that on the board. How we doing? So you start at the 6, right? So 6, 0, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. You start at that power, whatever that power is. Is that good? And then we put the x squared and the y to the 5th. X squared y to the 5th. X squared y to the 5th. All the way down the line. And then we just have to put the right powers on those. So we start at the 6th power. We'll go all the way down. 6, 5, 4, 3, 2, 1, 0. And then start at 0. 0, 1, 2, 3, 4, 5, 6. That's a very, what's the word, more systematic or real nice, clear pattern, right? A very clear pattern of binomial theorem. So, okay, you can write whatever you need to write on the 3x5 card for the exam next Thursday that help you out. There'll be a couple binomial theorem problems. So what do you guys think is the easiest way to figure out the coefficients? Do you like to do it by hand, by calculator, by Pascal's triangle? Remember, it repeats halfway, so you can just do your calculator. That might be easiest. Do your calculator, and remember when you get halfway, you don't have to do them all. It'll just repeat. So that'll save you some time. So yeah, so you want to just do, oh, remember the one with the 0 is always 1. Whenever you do any number, choose 0. You can't really do it. You can't really, you can put it in your calculator. It'll be 1. Just save time. It's always 1. The first one's always 1. Oh, and then 6 choose 1. That's always 6. Yeah, maybe I could speed you up. The first one's always 1. The next one's always whatever the number is. 6 choose 1 is just 6. If you want to save some time, don't even need to use your calculator. And then 6 choose 2. Use your calculator. Do 6 C2. It's going to be 6 times 5 over 2. Is that 15? And then 6 choose 3, 6, 5, 4 over, so is it 20? I think it's 20. You can use your calculator or, by hand or by Pascal's triangle. And now look, I'm halfway, huh? I'm halfway. Now, when I say it's going to repeat, yeah, you got to count it the other way. Sometimes there's 2 of the same number in the middle. Like sometimes there's another 20 and then 15, 6, but that's not right because I wouldn't get to 1. So on this, you got to end with 1. It's got to be a total mirror image. So sometimes there's 2 in the middle. It's basically when you have an odd power. There's 2 in the middle. You don't need to memorize. Just oh yeah, 15, 6, 1. Yeah, that works. Huh? So it'll always mirror like that. It'll always mirror across. Good. There, and then you do the other stuff. So x to the 2nd to the 6th. What's that? X to the 12th. I guess I don't really need parentheses anymore, huh? X to the 12th, and then just times 1 because y to the 0 power. Anything to the 0 power is just 1. It's not even a y there, huh? Everybody good with that? Because remember, 0 power means 1, not y to the 1. Just the whole thing 1. So that first term is just x to the 12th, not x to the 12y, just x to the 12th. Right. Good there. The first term. And then the second one is what? X to the 10th, y to the 5th, x to the 8th, y to the 10th, x to the 6th, y to the 15th, x to the 4th, y to the 20th, x to the 2nd, y to the 25th, x to the 0, y to the x to the 0 is just 1, so you can just get rid of that. Y to the 30th, there they are. There, it will not be multiple choice on the test. It'll just be, just leave. You just put it, as far as I'm concerned, you just put a circle around those and you're good. Those are the answers. Is that okay? Might racing ahead a little too fast. Questions I can answer on that one? Good. Are we extremely happy about the binomial there? Guess it's not a jump up for joy kind of thing. Is that okay? Any other questions or any questions at all? You guys are such a quiet group. I never know whether to race ahead or slow down. Give me some feedback so I know whether to speed up or slow down. Anything else I can answer on that one for you? All right, let's go to Sine at this point. Okay, so same thing. This one's 6th power again. So it's going to be very much like the last one. A lot of similarity. So 6, 0, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Like that. And then the two things we're talking about would be square root of x, and careful, negative root 5, right? You do need that negative sign on the root 5 with parentheses to various powers. That's important. Powers are 6, 5, 4, 3, 2, 1, 0, 0, 1, 2, 3, 4, 5, 6. The same coefficients we had before, huh? So take it from there. So we all good to there. That's pretty much just like last time, huh? Now we ready for the root stuff? So what is root x to the 6th power? Yeah, x to the 3rd. Everybody okay with that, right? Because, every 2 roots make a regular whatever, huh? So 2 root x's make a regular x. If you got 6 of them, right? If I got 6 root x is 4, 5, 6. So yeah, so root x to the 6 is that, and every 2 makes a regular x, huh? Yeah, so it's x cubed. That's totally right. We good with that so far? And then times 1, because anything to the 0 power is 1. So that first term is just x cubed. Second term now, what are we going to do with this root x to the 5th power? Yeah, so if we have 5 of them, let me erase one here and make this a 5. Yeah, so it's x squared and then an extra root x, huh? Does that make sense? Because we got 5 of them. So the first 2 make an x, the next 2 make another x. So that's x squared, and then the 5th one just has to stay root x, huh? So that'll be x squared root x. And then we have negative root 5. Kind of go off the screen. I think I'm going to need to write it over here. So this will be what? Putting it all together. You probably should put the... Well, it's fine with me. If you just circle that, you got full credit for me on the test. That's fine. They did a nice thing where they would put the 6 and the x squared in the front, and negative, and they would put the 2 root things together, root 5. That's probably the cleanest way to write it, but again, I'm fine. If you just circle what you got, it's good on a test. So there we go. I'm just rewriting it a little cleaner. Not required. Good. We'll try to keep going. Can you keep going on those other ones? Give you a second if they're all making sense for you.
So you just move the negative to the beginning of it because of the
Yeah.
negative root.
I just put the negative in the front, and I put the 2 root things together under a single root. Exactly. That's what I did on that. And the next one, what is that going to be? X squared, and then that's just going to be a positive 5, huh? So it'll be what, 75x squared? Let's get the next one okay. And then the root x cubed, what's root x cubed going to be? So it'll be x root x for that part, and then the negative root 5 cubed. Let's take a look at that. That would be negative root 5, negative root 5, negative root 5. 3 negatives, so that's going to be negative 5 root 5, because the 2 root 5s make a regular 5. Right, so it's going to be negative 5 root 5 on that. Does that make sense? So putting that all together, so I'm going to do the same kind of thing again. I'm going to move the negative to the front and put all the whole numbers together and then the root stuff together under one root, right? So 20 times negative 5, negative 100, x root of 5x. That good? And then coming on down here, root x squared, plain x, and minus root 5 to the 4th power. So if you have minus root 5, 4th power, 4 of them, every 2 make a regular 5, huh? Root 5, regular 5, root 5, regular 5, 25. So it'd be times 25. So 15 times 25. So
375.
375. Just did all this? Okay. Yeah. Max. Huh. Yeah, good. Good to there? Is this okay? And then root x. And what is minus root 5 to the 5th? It's going to come out negative, isn't it? negative, and if you have 5 of these things, 1, 2, 3, 4, 5. I know it's negative, so I won't even put in the signs. I know 5 negatives is negative. So negative, and every 2 makes a regular 5. Every 2, another regular 5, and then a root 5. So minus 25 root 5. Is that good? And then, then just again multiply the whole numbers with whole numbers and put the 2 roots together under a single root to be as clean as possible. If you want to have a clean looking answer, was it 6 quarters, $1.50 minus 150 root 5x. And lastly, 1, 1, and root 5 to the 6th, isn't that like 125? So that would be 125. There we go. This one was x cubed. So there's the terms. So that's the result of foiling that 6 times. The binomial theorem gives it to us. Questions I can answer? So that's basically it. Now in these last, 4 questions, 5 questions, they're going to ask you, they're just going to jump to certain places. They're going to say, all right, don't do the whole thing, just tell me the 5th term. Or just tell me the term that's next to x cubed, And that's exactly what I'll do on the test, because that way I don't use up too much of your time. I'll give you 1, give me the whole thing, like we just did on these last few. And then I'll give you 1, just, hey, tell me the 3rd term only, or tell me the term next to x to the 7th only, So let me show you about those. All right, so here's the binomial power thing they want. I would not want to do that by hand, right? X minus 2 to the 11th. I mean, that would take forever, and certainly I would mess up several times and get the wrong answer. So we're going to use the binomial theorem to just jump right to the answer, and actually, all they want is what's next to x to the 4th. So what I would suggest doing is just go ahead and begin by writing the pattern, and when you get to the x to the 4th one, just figure out that one only. That's the only one they want. So let's do it. So start with 11, 11, 0, 11, 1, 11, 2, 11, 3. You always start with the power, right? 11, 4. Now you might be thinking, well, isn't it the 4? It might be the 3 or the 5. I'm not sure. I just do a few of them, and then I'll do the next part. What's the next part? You put the x and the minus 2. Careful to use the minus sign, right? You need the sign in the front. So x minus 2, x minus 2, x minus 2, x minus 2, all the way down the line. And then you put the powers on. What's the power? 11. So 11, 10, 9, 8, 7, 6, 5. Oh, it's the next one, isn't it? I just need one more. I didn't realize. So I just need one more, don't I, to get it. So what would be the next one? 11, 7. Well, here, I'll do it over here. So 11, 7, x to the 4th. You guys with me? See how I just came up one short? Would it help if I put it down here? No, maybe not. Kind of out of room down there. Here. Yeah, I didn't realize I was going to come up one short. Let me squeeze it in. 11, 6, 11, 7, x minus 2, x minus 2. Powers 5, 4. So there it is. So there's the one. They wanted x to the 4th, huh? So there it is next to 11, choose 7. X to the 4th. Now what do you do with the minus 2? You put the powers on him also, starting at 0. 0, 1, 2, 3, 4, 5, 6, 7. So that's minus 2 to the 7th. We good? So that's the only term they want. They just want that one. So I just have to figure out what those numbers are. Multiply them together. So the 11, 7, just use your calculator. 11C7. 330. What is it? 330. 330. Thank you. And minus 2 to the 7, 128, minus 128? It's negative because odd number of negative signs. Is that good? And then finally, just multiply whatever 330 times, it's negative something. 330 times 128. No problem. 42, 240. x to the fourth. There it is. That would be painful to figure out by hand, right? Foiling 11 times and getting all the like terms correct, and it would be very hard to get that right. 42,240 negative. Is that good? Questions on that one? Let's make sure it's right. It's so big. I want to go back and type it in. I can answer on how we got it. So I just followed the pattern until I got to the one they wanted. All is well? All right. Last problem. Okay. So now they want the sixth term in the expansion of 3x plus 2. So we start at 10. Well, we start with a power. 10, choose 0. 10, 1, 10, 2, 10, 3, 10, 4. I think that's the sixth term, isn't it? First, second. Yeah, zero does count. Yeah. Fourth, fifth. Yeah, this is the sixth term right here. So here's the one we want. So let's put the rest of the stuff in and then just follow the pattern. Three x2, 3x2, etc. And you start at the 10th power. Then for the other one, you start at the 0 power, right? 0, 1, 2, 3, 4, 5. So there's the sixth term. So let's just multiply that all out and figure that out. That's the one they want. So it's 10, choose 5, 3x to the fifth, 2 to the fifth. So 10, choose 5 in your calculator. Somebody have that one? 252, thank you. And then 3x to the fifth will be 243 x to the fifth, and 2 to the fifth is 30. It's going to be a whopping number. So see how I'm figuring all the little parts out there? So 252 times 243 times 32. Anybody got that? That big. Oh, 195. 1959552. Thank you. X to the fifth. 1 million. Wouldn't want to do it by hand. 1,959,552. X to the fifth. That's what I thought. I'm just kidding. That would be really hard to figure out by hand. Is that good? It's amazing it gets that big, huh? Just from 3x plus 2 to the 10th. You know, writing 3x plus 2 10 times and foiling it all out and gathering like terms. It gets big. Think you might mess up by one number somewhere along the way there?
Maybe just one.
Well, I'm getting home. It's almost to 2 million. I'm going to type it in. I can't believe that's right. 1,959,552. That one. Is that one okay? Because that's the end now. We're going to turn to trig. That's the last topic in the course other than trigonometry. And you've had trig before, right? It's going to be a review, basically, of what you've done in some of your trig stuff. All right, so the binomial theorem. All right, so you all had trig, and it was your favorite class, maybe. And we're going to review it. It's good to see it a second time, you know, especially before you go into calculus, just to have a second look at it, refresh your memory, and because it is used Not a lot in Calc 1, a little bit, and then a lot in Calc 2 if you're continuing to go that way up a whole bunch. My daughter's doing Calc 2 this semester. Mr. Dorn, I think I mentioned that a couple times, and she was just the other day saying, man, so much trig, so much trig. She's really learning her trig now. That's where you really learn it, when you got to use it later on. All right, so there's a point on the unit circle, P. It's that point. And we're going to talk a lot about the unit circle. Yeah, I'm sure you've heard of it. Why do we call it the unit circle? What do we mean, unit circle? What does that mean? It means one. Unit means one. It's the circle of radius 1 unit. So whenever we say the unit circle, we mean like the radius sideways or up or left or down or whatever. It's 1 from the middle to the edge anywhere. It's the circle of radius. So it's just a really convenient circle, easy to use circle. That's all we're doing. Super convenient. Just 1 radius. Okay, so the unit circle, and they're giving me the point P, which is right here, kind of. And they're saying it's what? Root 21 over 5, comma, minus 2/5 on the screen there? Yeah. Okay, so what does that have to do with sine? And then they're going to ask me all the trig functions. So how do you figure out the sine from a point, P, on the unit circle? What's the deal there? What does the sine, cosine, tangent, stuff like that have to do with points on the unit circle? Do you remember? Anybody have Mr. Bigham for trig? Mr. Bigham? He's a lot of fun, isn't he? I have all my kids take Mr. Bigham. He's the funniest guy in the math. It's almost like a stand-up comedian, huh? Throughout the course, he could be a comedian. So, if you had trig here recently, maybe anybody remember how did points on the unit circle go with trig functions? Do you remember that the x coordinate? My thing's jumping around. Did it jump around the screen when I do that? No, it just stays there. Anyway, the x coordinate's always cosine, and the y coordinate's always sine. So when they ask like sine, they basically just want the y coordinate. So minus 2/5. And then cosine's the x, so that'd be root 21 over 5. Like that. Oh, I'm getting a little flicker, huh? And then tangent is always the y coordinate over the x coordinate. So you just take the y coordinate minus 2/5 over the x coordinate, root 21 over 5, like that. Coming back a little bit, remember this kind of stuff? So sine's always the y coordinate, cosine's always the x coordinate. And now what do you do with, how do you simplify tangent y over x? So I get a fraction over fraction. How do you simplify a fraction over a fraction? Yeah, we give it a flip. We're starting from the ground floor here, so if you're feeling like, oh man, I don't remember how anything, that's okay. We're starting from assuming nothing. So we'll start from the beginning. So minus 2/5 times 5 over root 21. That good? Remember the bottom fraction flips up, and the 5's just cancel, huh? So you get minus 2 over root 20. That's almost the answer. What's the only little issue we have with roots on the bottom? You can never leave roots on the bottom, huh? So we're going to multiply by root 21 top and bottom. We'll get minus 2 root 21 over plane 21. So there's the tangent. Bless you. Is that okay right there? Because the 2 root 21s on the bottom made a regular 21. So there's the tangent. So now coming back a little bit. So sine, again, is always the y coordinate, and cosine is the x coordinate. And then tangent y over x. What about the other three, like cosecant, secant, and cotan? Do you remember? They're upside down, aren't they? They're just the upside down. So do you remember which is which? So you can put it on your 3x5 card. You don't need to memorize it. You know, you'll have your 3x5 card. So what's the upside down of sine? Anybody remember that one? It's the cosecant one, isn't it? Yeah, cosecant is the upside down of sine. So it's 1 over sine. It's just the reciprocal, we say officially. Flip it. So it'd be just minus 5/2, huh? So there's cosecant. Just flip the sign. And then the upside down of cosine is secant. So it's 1 over cosine. It's the upside down of cosine. So that'll be 5 over root 21. We can't leave it that way, though, huh? because that would be a root on the bottom again, you know. So we got to get rid of that. So multiply top and bottom by root 21, and you get 5 root 21 over plane 21 for the secant. And last is the cotan, which is upside down of tangent. I'm kind of running out of room. Do it up here, I guess. Cotan is 1 over tan. So it's going to be upside down. Now here's tangent. So it's going to be that upside down. So 21 over minus 2 root 21. Yeah. And you can't, there we go to there, can't have a root on the bottom. So, same thing, you know, we've done this a couple times. So multiply top and bottom by root 21. Get 21 root 21. Kind of getting messy here. Can you guys read that okay when I write over other words and things? It's not the easiest. Let me know if you can't read something. I do it all the time. And you think, what, is this like a new thing? Well, I was actually just talking to the dean the other day who reviewed me, and she said, one thing is if you could somehow write so it's not over the other stuff. So it made me think, yeah, it's tricky to do it. Yeah, I could go to a blank screen, but then we wouldn't have a question. You know, I could go, okay, yeah, let's write on that screen, but then you wouldn't have the question. So anyway, just you let me know. What works best for you. So everybody see what happened on the bottom there? Root 21 times root 21 is plane 21. Everybody see that? What happened there? The two root 21s, you know, made a plane 21. And then these will just cancel, huh? So I get root 21 over minus 2. That's the cotangent. So we got all 6 trig functions. Question?
Is it easier just to do the opposite of tangent? Because they're going to use...
I did do the opposite.
Well, no, what I'm saying, instead of going from...
Oh, just from right here?
Yes.
Totally. Yeah, that might have been easier. Yeah,
Not always
pretty close.
Okay.
That'll work. That'll work great. Yeah, cotangent is going to be x over y.
Right.
Totally. Yeah, you can do it that way. Yeah. Other questions on that one? That would have been easier, huh? Because you wouldn't have had to mess with the roots on this one. But on other ones that don't have a root in the bottom, the other way would be easier. Yeah. Okay. Anyway, it'll be the same either way. Everybody good? So again, the moral of the story, the main point, cosine is the x value. So they're kind of reversed. We always think of sine as coming first, huh? Which it does in the list. You know, it's always sine, then cosine. But in the coordinates, it's cosine first. You got to kind of intentionally remember that. The x is cosine. The y is sine on that. And then the rest, all the other 4 trig functions come from the sine and the cosine. Did you notice that? Right? Cosine is x, sine is y, and then all the rest just come from them, don't they? Right? The tangent is y over x, and you know, on you go. So really, it's all about sine and cosine. It's really just all of trig is about sine and cosine, really. All the rest just are various manipulations of sine and cosine. Okay. All right, so the tangent of 14 pi. Tangent of 14 pi. So this is question number 3, tangent of 14 pi. So that's a little tricky. How are we going to do that? Now notice it says find the exact value. Do not use a calculator. So again, I want to remind you on part 1 next Thursday. Let me write it instead of just say it. Part 1 of exam 4 is going to be no calculator at all. Well, if I'm being clear on that, nobody will be shocked and surprised, right? None at all. None at all. No graphing, no regular, no nothing. Just the trig, though. All of it's going to be on part 1. Part 1 is trig only. Trig only. Nothing else. So all the other stuff we did with sequences and all that, you'll be on part 2, and you can use your graphing calculator and your regular. Use a lot of calculators if you want, you know. But the trig stuff, because I do want you to learn the trig stuff without a calculator, because it's important when you go into calculus. I mean, you can use a calculator in calculus, but that you know how to find the values, because we do something called limits. And limits, you have to understand the flow, like the direction that things are headed, which you won't understand if all you did was push buttons, you know. So anyway, so that's why, and I'll carefully show you how to do all that. And you will have your 3x5 card, so you can write a bunch of things down as well. But I still want you to be looking at a unit circle and figuring out where they are on the picture. So when you get to calculus, you do limits, you'll have a feel. Because limits are a direction, they're not just a button push thing. So anyway, that's the reason. So let's do that then. Let's do this without a calculator. So how do you do, so 14 pi, that's a, when they throw the pi in there, that's a, remember radians? That's a radian angle, huh? It's called, remember radians? No, it's not degrees. There's two ways to measure an angle. What is an angle? An angle is an amount of opening between two lines, huh? So an angle is an amount of, like I can open the door at the hinge here, a certain angle. There it's open a certain angle, you know. So that's all an angle is an opening between two lines. And you can measure that opening in two ways. Well, there's also gradients, but anyway, we're just going to talk about degrees and radians. Degrees and radians. So how's that work? Let's talk about degrees first off. So if you have a circle, how much, we started here at 0 degrees. They just made that up. They could have started right at the top at 0 degrees. It was just made up. They just said, we'll start over here at the right. That's 0 degrees. And when you get straight up, how many degrees is that? Yeah, this is 90. This is a 90-degree right angle, huh? So you've opened up, from there to there is 90 degrees, huh? Now hold on. Why is that 90 degrees? How far is it all the way around? 360 degrees all the way around. Why? Why is it 300? Is there like a logical reason for that? You know, it has to be 360 because of this? No, is the answer. They made it up. They just made it up. They could have said all the way around, it's a nice, clean, even 100. Sometimes I wonder if that would have been easier, you know? Just, why 360? How about just a nice, all the way, it's a complete circle. How about a nice, clean 100 or maybe 1,000, you know? Why 360? I mean, how about 247? I mean, where do they come up with 360? It just seems like a little bit unclean. I mean, it's not terrible, but why is all the way a 360? You know why? It's actually historical. They basically just made this up. Remember, math is made up to describe things that are real. What do you know? I bet you can come up with if I say a couple of hints. What do you know that goes all the way around and about 360? Not quite 360. Yeah, the calendar. We rotate around the sun. Back when they first were doing angles, I don't know the days, you can type it in Google and get it in seconds, but they were using it to navigate ships by looking at the stars, and their best estimate of our rotation around the sun was 360. So probably about 1500s after Copernicus first realized that the sun's not going around us, we're going around the sun, right? So they were estimating. Now we know more accurately. It's closer to 365 days for us to go around the sun. So they used 360 because they thought, well, that's about a full circle. That's it. So they just made it up. So my main point is they just made it up. They just said, well, 360 will be a full circle because that's pretty much close to what we're doing around the sun. And so then everything else comes from that. Then half weighs 180, a quarter weighs 90, on all the angles that we're used to. So that's the degree system, degrees. How about radians? What's all the way around in radians? 360 degrees, how many radians? 2 pi, yeah. 2 pi in the radian system. Halfway around then is, and again, they made that up too. So, well, that's not entirely true. Is that true? Trying to think for a minute. No, that's not true. You guys know what radians are? Radians are an actual distance in the unit circle. Here's what I mean. How far around, like if you're a little person or a big person, if you're a little ant and you're going to like walk around the circle, actually cover the distance around the circle, right? How far around is a circle? A circle of radius 1. Remember this is a unit circle, radius 1 circle? How far around the outer edge of a circle is if you could open that up and stretch it out, that circle, if it was a wire, it was a round wire and you stretch it out, how long is that? Remember the formula for how far around the outer edge of a circle from geometry? 2 pi r. Good, whoever that was, good memory. That's called the circumference. Anyway, you're not going to be testing any of this. And I'm going too far with theory here. I just get into this and I got to get some homework done. All right, so 2 pi r. This will be my last little thing. All the way around the outer edge of a circle is 2 pi r, right? What's the radius of the unit circle? 1, right? So it's 2 pi times 1. In other words, it's 2 pi. So 2 pi is actually the distance around the whole circle. That's what radians are. Radians are actual distance. So actual distance around the unit circle is 2 pi. So that's what the radian system is. It says when you open an angle, if your radius is 1, how far would that actual distance be? That's what a radian angle is. Degrees are based on 360. All right, so those are the main two systems that are used, degrees and radians. And so, with a little bit of history there. So now, getting back to it. So how do I convert? How do I take this? How do I take this 14 pi, which is in radians, right? Because it doesn't have, how do I know it's in radians? It doesn't have a degree symbol. If it doesn't have a degree, even by the way, guys, this is what surprised a lot of people. Even if they gave me the 14 without the pi, a lot of people think, well, when you see the pi, you know it's radians, which is, I know what you mean. That's pretty much almost always the case. But technically, it's not. Even if they gave me 10 to 14 with no degree symbol, that would actually be radians as well. Really, the technical difference is there a degree symbol or is there not? So anyway, just be a little careful with that. I think there's like one question, I think it's in 6.3, where they try to trick you. And they throw in 14, they don't put the degree symbol. You know, and you use your calculator and you hit the degree button and it's not coming out. Well, it's because it's radians. If the degree symbol's not there, it's radians. It doesn't have to have the pi, although it almost always does. Huh? Anyway, getting back to it. 14 pi, this is radians because there's no degree symbol. How do you convert from this radian angle to degrees? Because I just think better in degrees myself, more naturally. I think most people do. In degrees. So how can I convert this 14 pi to degrees? Do you remember that? Remember what you do with the pi? The pi right here is 180 degrees, isn't it? Because it's halfway around. So pi radians is 180 degrees. So basically you just stick in the 180 degrees where the pi symbol was. That's what you always do to convert from radians to degrees. Just put in the 180 in the place of pi. Somebody have a calculator? What's 14 times 180? Well, actually, yeah, that's right. You can't. No, good point, Carissa. You are totally right. I just said you can't use a calculator. Does anybody have a calculator? Yeah, so let me hold on. I'm being a hypocrite here. I've got to do this without a calculator since I'm making you do it without a calculator. Yeah, how should we do this? 14 180s. So that's halfway around 14 times, right? So halfway, once, twice, 3 times, 4 times, 5 times, 6 times. So you get the pattern. What's going to happen when I go 14 times around halfway? That's 7 full times around. In other words, where am I going to end up after all those 7 full times around? Right where I started. This is the same thing as 0 degrees. Isn't it? 14 pi is 7 2 pi's. 7 full circles. So you're going to be back where you started. You with me? I'm in a mess out of this. Let me clean it up a little bit. But yeah, so when all is said and done, I hope I'm making some sense out of this. When all is said and done, we're back here at 0 degrees, right? Because that's what 14 pi is the same as 0 degrees, right? Because it's 7 full circles. So what then? Well, they're basically asking me the tangent of 0 degrees. So how do you do that? Well, you find the coordinates. Remember, sine is the cosine is the x and sine is the y. So what's the coordinates of that dot right there? Like how far over, how far up is that dot? So this dot right here is over 1, up 0. We all agree? It's a unit circle, right? Over 1, up 0 is that dot right there, right? And the cosine is the x, the sine is the y, right? So when they ask me tangent, what is tangent? Sine over cosine. 0 over 1, 0. So we figured out the tangent without using a calculator. Does that make sense? You find the dot on the unit circle. Is that good? Is that making sense? Questions I can answer? Yeah. No. Yeah. It's the same spot. Yeah, whether you say 14 pi radians or whatever that degree is, some giant degrees, it basically all that matters is where the dot ends up after all the rotating of the angle. Yeah, so the angle is just how far you rotate in either radians or degrees, but it's the same amount of rotation. So it's 7 full circles in either language, in either radians or degrees. So you end up back where you started for this one. And so that's what matters in the end is the coordinates of where you end up. Or if you meant, do I care in the test? I don't care at all. how you got there. That good on that? All right, let's try. Okay, so draw yourself a unit circle. And then you got to take that, unless you just think really well naturally in radians, then that's fine. Go ahead and just find the spot that is at the angle negative pi over 2 radians. But probably for most people, it'd be easier to change that to degrees. How do we change that to degrees? What do we stick in for pi? 180. Yeah, so remember that pi radians is always 180 degrees. It's halfway, right? So this is a cotan of minus 180 over 2. Which is cotan of minus 90. We good? So where's minus? Now, what do we do with a negative angle? What does that mean, a negative angle? We always start here, right? Here's the 0. We always start there. They just made it that way. They just made it up. We could have started somewhere else. They just made that up. Start there. And positive means open up, huh? Negative means go down. So negative 90 means go down. Negative 90 is boom, right there. There's negative 90 degrees, huh? It's this dot right there, which is now off the screen. There we go. Is that good, how we found that? That's negative pi over 2 radians. It's negative 90 degrees. By the way, it's also the same as what positive angle? If you went the other way, this way, and ended up at that same dot, what angle would that be? 270, or yeah, in radians it's 3 pi over 2 radians, if you're comfortable with radians. Anyway, I just want to show you that there's different ways to say the same ending location. Terminal side is the language they use sometimes. This is the ending spot, said many different ways. Said negative 90, negative pi over 2, or positive 270, or positive 3 pi over 2 radians. It all ends up right there, huh? So really, all those angles are going to end up with the same spot. So all those angles are going to have the same 6 trig functions: sine, cosine, tangent, secant, cosecant, cotan. Does that make sense? It's all about the dot you end on. Okay, so write down the coordinates for that dot. Right, the parentheses x comma y. Can you do that real quick? So write down what are the coordinates of that dot. How far over, how far up and down. So that dot is over 0, down 1, right? And the cosine is the x. Remember, they're reversed. Cosine comes first. Cosine is the x. The sine is the y. Okay. And what is cotan? Yeah, it's cosine over sine. It's the upside down of tangent, huh? So cosine over sine. We good? So that's going to be a 0 over minus 1. 0. And we got it. We got it without using a calculator. And that's important to understand it that way because of limits in calculus. You need to know like where the thing is and have a feel for what's happening, not just hit the button. Questions I can answer on that? That good? So you can put all this on your 3x5 card, you know. Put your unit circle, put some values, put the definitions of sine, cosine, tangent, you know.
Is cosine over sine equivalent to 1 over tangent?
It is, yeah, because remember, tangent is sine over cosine, so 1 over tangent would be the flip of that. Cosine over sine, which is cotan. Totally. Good. All right, they want the sine of 45 plus the cos of 60. Notice they say exact answer, no calculator. It's exactly what I'll ask you for on part 1 next Thursday. You can use a 3x5 card and put anything you want on there. And I would definitely put the unit circle. But no calculator, and I want exact answer, meaning I want like root 3 and not a decimal. And so does the Math Excel program. So how do we do that? Well, how do we find these weirder, stranger angles now without using a calculator? Well, it's the unit circle. Let's go to the unit circle again. Hey, by the way, have you ever thought about this? I thought about this after I was a trig student, years after when I started becoming a trig teacher. I remember it just was funny. It occurred to me, if somebody had come up to me on the street after I first finished, pre-calc and I knew trigonometry, and somebody had said, hey, you're taking one of those college-level math classes. What is the sine or the cosine or the tangent? If they'd asked me, what is it? What is the sine? What is the cosine? And I would say, well, what do you mean? I would probably say, what do you mean? Do you want me to do the sine of 45 degrees or the cosine of 60 or whatever? I could do them. I could do them. I knew my unit circle and how to do them. I give you answers. But if they said, no, I don't want an answer. I just want you to tell me, what is it? What really is the sine and the cosine? I would have said, I have no idea in the world. I can crank some answers out. Does it ever occur to you that it's strange sometimes that you can do some things in math and have no idea what they are? So if I was to ask you, what are these things? Would you have any better answer than I would have had? I would just have said, I have no idea. It's some math thing. You know what they are? Remember, they're made up. Remember how math fits in the real world? I want to keep that before your eyes all the time. Remember, it's made up. So trig as well. It's made up, sine, cosine, tangent. The unit circle thing I'm showing you, that's just made up. That's just a nice made up way to get values. That's not really what it is. That's how you can get values. But what is it in the real world? It's made up, so I should say, what does it describe in the real world? Because it's not something in the real world. You can't taste or touch sine and cosine like you can this table. This table's something in the real world, right? What does sine and cosine describe in the real world? Anything that rises and falls, and rises and falls, which is tons of stuff in real life. So, for example, the alternating current coming out of the wall right over here, right? The plugs, what comes out of that wall is, 120 volts, and the current is alternating, AC. That stands for alternating current, which means it's a sine wave. The current rises and falls that comes out of the wall, whereas a battery is DC, direct current, is flat line. Anyway, that's one thing. So whenever electrical engineers do stuff with circuitry and they want to set up some kind of system, they know that is represented by sines and cosines because it's not just steady all the time. The current rises and falls, rises and falls. I really don't know why. I don't know any more than that, but I know it does. I know it rises and falls, rises and falls. And how about when I go to the beach, I take my family to the beach, I want to look at the tide charts to find out when the tide is out so we can go grab the little shells, right? What predicts that? Well, what does the tide do? It goes out and it comes back. It goes out and it comes back with the moon, right, pulling the waves around. So, how do you make up a math function to predict where the tide is going to be? Sines and cosines, right? All kinds of things in real life, all the stuff with the planets and the orbits and all of that. All of them, right? They pass around. They come closer and further, closer and further. We go around the sun, on and on and on and on. Moon goes around us, right? All kinds of things in real life rise and fall, cyclical. So anything cyclical in real life can be represented by trig functions. That's what they're for. That's why they made it up. Engineers and physicists and people started dealing with things in the real world that were cyclical, and they said, we need some kind of function to represent these cyclical things. They made up trigonometry. That's exactly what sine, cosine, tangent are. Made up things that are cyclical. So, one good way to represent them is the unit circle. It's just, that too is made up, but it's a good representation, right? When this dot goes around the circle, what does it do? It rises, right? It rises and falls. It rises and it falls, right? As your dot goes around a circle. All right, so how do we do other values now other than the memorized ones on the unit circle? Let me give you the information. So, right here's 90, right? And this is 0. In between, what's right in the middle between 0 and 90? 45 degrees, halfway between 0 and 90, right? Right here and right here, we have 30 degrees. Let me write it in here. Yeah, let me put it back. 30 degrees and 60 degrees. Basically, what we do, how trig is usually learned, is we memorize 3 values inside of every quadrant. 30, 45, and 60. And then we'll memorize, they'll be the same spots. 3 values in this quadrant, 3 values in this quadrant, 3 values in this quadrant, and of course the axis points, which are just zeros and ones, as we've seen 2 of them already. And the rest, you use your calculator. So that's what I'm going to expect, same thing, that's pretty much what everybody does. Well, I know some teachers just let you use a calculator all the way. But this is what's normally done, and this is what I'll expect on the exam next week. Just memorize the 3 spots. You can write them right on your 3x5 card, so have them written down. 3 spots in every quadrant. I would encourage you to memorize those. I'm going to show you a real easy way to remember them. And then it'll be helpful when you get to calculus because you'll need limits. All right, so how do we remember them? Well, what I'm going to do to help you is small, medium, and large, like ordering a soda. And it's going to be square root of 1, square root of 2, square root of 3, small, medium, and large, and put them all over 2. So square root of 1 over 2, square root of 2 over 2, and square root of 3 over 2. That's the small, the medium, and the large for finding spots on the unit circle. Now, I realize that square root of 1, what's the square root of 1?
1.
Yeah, so this is just a half. But I just wrote it with a root so you can see the pattern easily. Root 1, root 2, root 3. But root 1 is really just 1, so that's really a half. So really the values are a half. Root 2 over 2 and root 3 over 2. But the pattern is easy. Root 1, root 2, root 3, small, medium, large. Now, what am I talking about? Well, say we're at this right here. And we want, well, actually, they want 60. Let me start with this one. They want cosine of 60 degrees. So I'm, okay, there's the 60 degree spot. They want me to do the cosine there. Well, what you want to do is go to that spot and then go over, and straight up. Like an x and a y coordinate, you know? I want to deal with the xy coordinate here. Straight over, straight up. Notice that it's over, and it's up. It's over a small amount. And it's up a large amount, isn't it? To get to that 60 degree angle spot. Right? Because it's almost to 90. It's almost to the top up there. So it's over a small amount, up a large amount. The one in the middle, the 45, that's over a medium, up a medium, because that's in the middle. And the one over here is over a large amount, only up a small. And the small, medium, large are these guys. Boom, that's it. You can get all the values now just from that information. Just think small, medium, large, and these are the small. Just put these on your 3x5 card. You can find sines, cosines, and tangents, and the other 3 as well. Any of these 3 spots around the whole unit circle. So let's get to particulars here. So again, getting back to the 60 degree here, over the small amount, up the large amount. So that's over the half, up the root 3 over 2, because that's the small and the large, right? Small is 1, medium is 2. Well, root of 1, root of 2, root of 3 is the large, over 2. So the coordinates of this point is over a half, up root 3 over 2. Does that make sense? And the cosine is always the x, and the sine at that degree spot is always the y coordinate. And then the tangent is sine over cosine, and then the other ones are upside downs, right? So what do they want? They want cosine of 60. So what's the cosine of 60 going to be? At the 60 degree spot, over a half, up root 3 over 2, x, y, the cosine is the x. It's a half. Cosine of 60 is a half. Okay, great. What's the sine? What's the other one? What's the sine of 45? So the one in the middle, and that's the same thing for the middles all the way around the circle. The middles are always medium with medium. Medium always goes with medium, and small and large go together. So the ones in the middles, the 4 middles all the way around, those always are medium, medium. All the other spots are small, small with large. So let me clean this up a little bit. Get rid of this.
So the 30 is large, small?
Yep. So the medium over medium up medium. So this is medium, medium to get to the 45 because he's right in the middle, huh? Medium is middle. So over, and what is medium? It's the root 2 over 2, right? Because it's root 1, root 2, root 3. So the medium is root 2 over 2. So it's over root 2 over 2, up root 2 over 2. The coordinates of that point, the x and the y, are over root 2 over 2, up root 2 over 2. And remember, the cosine is the x, the sine is the y. So what's the sine of 45? root 2 over 2. So they want sine 45 plus cosine of 30. They want root 2 over 2 plus 1 over 2. There we go. We gave them what they wanted without using a calculator. So that's how we do trig. We memorize those 3 spots in every quadrant, and the rest we use a calculator. Any spot, like if they ask me 31 degrees, I'd use calculator. Just use calculators for the other spots. But memorize these 3, and it is valuable to memorize those 3 because then you know a trend. You know where things are headed for limits in calculus. Questions on that one? All right. So sine 60, cosine 30. So again, just draw ourselves a unit circle. Here's 30. Here's 60. 45 is the middle.
Was that last one how you wrote it out at the end? The 2 fractions is not the simplified form? Or would you have to put the...
So this one here, yeah, we can't really simplify. You could make it into 1 fraction like that. I don't care on a test. Either way is fine. Like that, you could do it, but yeah, there's nothing. You can't add the 1 and the root 2, right? Because they're unlike. Remember those rules from algebra? Yeah, so they can't combine together. But anyway, on that. All right, so see if you can find the sine of 60. So looking at the unit circle, over and up. It's over a small amount, up a large amount, right? For that 60. So it's over a half, up root 3 over 2.
No, it's just multiplication.
Yeah, they're good. This is multiplication, huh? Because there's no plus or minus between them. So, so remember the cosine is the x, the sine is the y. So they want what? Sine of 60. So that's root 3 over 2 for the sine of 60 times, yeah, it's times, so that's multiplication. Cosine of 30. Everybody good so far with the sine of 60? Now, do the cosine of 30. So go over large amount, up a small amount, huh? To get to 30. Over large amount, up a small amount. Over the large, what's the large? Root 3 over 2, up a half. So the coordinates here are over root 3 over 2, up a half. We good there? And then what is this? Cosine is x, sine is y, always. Remember, they're reverse. And they want cosine of 30, so they want root 3 over 2 again. Turns out they're both root 3 over 2, huh? Multiply those together. What's root 3 times root 3 on the top? Plane 3, 2 times 2 is 4, 3/4. Good on that? Questions on that? If I move on? All right. Okay, so they're giving me secant and cotan. So one of the important things to remember then is what those are. You put those in your 3x5 card. You know, does anybody remember? What is secant? Secant's the upside down of something, huh? What is secant the upside down of?
Cosine.
It's cosine, yeah, do you know that? So that's 8 really times 1 over cosine pi over 3. And cotan, you can put 1 over tan, but you're still going to have to write out what tan is. So you might as well just go, look, it's cosine over sine. Is that okay if I just do cotan that way? Remember, because tangent is sine over cosine, and cotan upside down is cosine over sine, right? So I just wrote cotan as cosine over sine of the angle, whatever the angle is, pi over 4 in this case. So we good to there with the first step. Just break them down into sines and cosines. See, it's all about sines and cosines, isn't it? All of trig is about sines and cosines. And all sines and cosines are functions that rise and fall, rise and fall. That's all this is for. Okay, so now draw your unit circle. Oh, let's turn those into degrees, huh? Probably easier. I mean, you don't have to. If you're good with radians, you just know where those are. Great, just go ahead and work with it. I found, and I myself prefer degrees. I think better with degrees. So you stick 180 in for the pi if you want to convert it to degrees, right? So pi over 3 is 180 over 3. It's 60. You can do that without a calculator, right? 18 divided by 3 is 6. And then pi over 4, 180 over 4. When you cut something divided by 4, that's dividing it by 2 twice, isn't it? So take 180, cut it in half. What do you got? We'll do this without writing anything, without any calculator. 180, cut it in half. 90. Right? Cut it in half again. 45. It's got to be 45, doesn't it? So pi over 4, and you might just know that. Pi over 4 is 45 degrees. You remember from trig. Pi over 3 is 60 degrees. All right, so what they're really asking then, this pi over 3 angle is 60. And the pi over 4 is 45. Good? All right, draw yourself a unit circle. Find those values. Can you already tell what the cosine of 45 over the sine of 45 is? Just picture where that's at on the unit circle. Picture the x and y coordinates. It's a medium, right? It's got to be 1, doesn't it? See how you're starting to really sense trig now? Because you're picturing it more. That's way more valuable to your future of using trig in calculus. Alright, let's draw a unit circle. .45's right in the middle. Well, just do the 60 first, huh? So there we have our 60, and I'm kind of off the screen. So over a small amount, up a large amount to get to that 60-degree angle. And so that's over a half, up root 3 over 2, right? Remember, small, medium, large, root 1, root 2, root 3, over 2. So that means that point is over a half, up root 3 over 2. Cosine is the x, sine is the y. Remember, they're vice versa. What do we want? We want cosine of 60. So we want a half. So this is 8 times 1 over a half, and then you flip that up, it's going to be 2 times 8, 16, right? For the first part. Everybody see what's happening there? So we got that cosine of 60 as a half. The more you do this, the more you'll be able to just picture these. You know, so I'm going to say cosine of 60, you can just picture the unit circle in your head, just go, oh, that's up here, cosine is over small amount half. You just know the value right away. Good. That will happen for you if you keep working with trig. So anyway, so this is 8. Flip up the half. It's 2 over 1, so it's going to be 16 for that first part. The rest is going to be 16 plus whatever. All right, so then we're ready for the other one now? We good with that? Let's do the other one. The other one's right here at 45 degrees. Right here in the middle. 45 degrees. So that's going to be what? Over medium, up medium, over medium, up medium. 45 is right in the middle, all the 45s in any quadrant. We're going to start moving them to other quadrants here in a second. So he's right in the middle, medium, medium. So notice medium goes with medium, and the small and large always go together, huh? Medium never goes with large. Medium never goes with small. Medium just goes with medium. It's right in the middle, and the small and large always go together. All right? So that, and what's the medium? Root 1, root 2, root 3. So it's root 2. Oops, root 2 over 2, and root 2 over 2. So that's over medium, up medium. Cosine is x, sine is y, so they're both the same thing, aren't they? I mean, if you want to be all formal, you could write them both out, but you know it's just going to be a big old 1. So 16 plus 7, is that 23? And we got it. Is that good? No questions? All right, and also I could also advertise. I feel like I need to defend my no calculator policy on this one. Also, if you take Mr. Dorn, that's who my daughter has right now, he has no calculator on several of the tests, at least in Calc 2. I don't know what he does in Calc 1. So she's happy now that I forced her to memorize the trig values because she has to. Going real far into other quadrants. 17 pi over 4. So they want all 6 trig functions, don't they? Yeah. Sine, cosine, tangent, secant, cosecant, cotan for 17 pi over 4. So first thing is to find out where in the world is 17 pi over 4. So what do? How do you convert that radian to a degree? What do you do? What do we put in for pi? 180, right? So it's 17 times 180 over 4. Now you're going to have to do that by hand calculation, which Carissa can do. So I would divide first, because that makes numbers smaller. You don't have to. You can multiply first if you want to. But it'd be a little quicker, a little easier if you divide first, because divide makes things smaller than multiply afterwards, but it'll work either way. So 180 over 4. Can we just do that one in our head? So 180, just 180 over 4. So you just take half of it and half of it again. That's how we quarter something. Half of half. So what's half of 180? 90. Half of 90? 45. So this is just 17 times 45. And then you just write that out and do it. 17 times 45. Yeah, if you know more advanced, I'll show you other ways. But this is worst case scenario. You can do this at least. So 17 times 45. 5 times 7 is 35. Oops, I'm kind of getting scribbly here. 28, 23, 31. Add a 0, 45, 6, 765 degrees. So we converted that to 765 degrees. Where in the world, so if I do the unit circle, you know, and do the circle, where in the world is 765 degrees? How do we find it? What's all the way around? 360. So subtract 360. Subtract a full circle, huh? Then you've got 405 left. So you go a full circle, and you got 405 left to go. So you go another 360. And you got 45. So then it's 45. So it's 2 full circles and a 45 is what it is, isn't it? Does that make sense? 360, another 360, and 45 more. So really it's the same thing as just 45. They're really just asking, what's the sine of 45 degrees? That's the same spot. They just did 2 full circles before they got to the 45. So what is the sine of 45? Root 2 over 2. It's medium, medium, right? Over medium, up medium. Right? Now I don't want to do any more. I just want to find the angle. You could do the rest, right? Easy enough. All the other trig functions, right? It's medium, medium at 45. We good with that? Questions on that?
Can you do the top as 8 full circles, 1/2 circle divided by 4?
Say that again?
Like 17 180s would be like 8 full circles, right?
Right.
And then 1/2 a circle.
That's true.
So then would you be able to do like 8 full circles divided by 4 would be 2?
Yeah.
And
Yeah,
then
I like what you're
1/2
saying.
circle divided by
Yeah,
4
you're right.
would be a
You're right.
fourth of the circle.
Correct, yeah. Yeah, so there's other good ways to do it, totally. Yeah, one thing you could do is you could just pull that, let me say what you're saying and just kind of pull that right to the front, because I like what you're saying, Chris, you're right. You could just pull that 17/4 to the front. Yeah, there's some other options. And that would be what, 4 1/4, right? If you do mixed numbers, 4 times 4 is 16, add 1, so that's, right? So that means, now, remember, so that's 4 pi plus 1/4 of a pi, right? 4 1/4. 4 1/4 pies is 4 1/4. So 4 pi is 2 full circles, and then pi over 4, right there. What's another way? Yeah, whatever. There's a million ways. Whatever way you want. So secant of 74 degrees. Oops. What is secant the upside down of? Do you remember? That one's cosine. You can have those in your 3x5 card. So yeah, so it's 1 over, because you probably don't have a secant, but you might. Some of the calculators have those now. Many of them don't, though. So in case you don't, just 1 over cosine 74. Yeah, that's not one of our memorized spots, right? You know what I mean? Right? What do we memorize? We memorize 30, 45, and 60. So 70 and 90, of course, is straight up. We don't memorize 74. That's between 60 and 90. That's not one of my memorized values. So that means just use the calculator, hit the buttons. So, and then take 1 over that and round the answer to 2 decimal places. Somebody got it? .62 places. 3.63. Were you in? Make sure you're in. What is it? Degree mode instead of radian mode. Yeah. So make sure that you're in degree mode. You know the modes. That's an easy mistake to make. Make sure you're in the right mode when you do those in the calculator. Okay. So we get that 3.63. The final answer. Anybody else getting the same number? Nobody.
So how do I do it? Maybe it's because I'm not in degree.
I've only got one person so far. Nobody else getting that number? Get it? Okay, good. Looks like it's right. 3.63. You good? If you have trouble, grab me after. Be glad to help you.
Is this not the right way to do it?
You check your mode. You must be in radian mode.
How do I do it?
Hit your mode button.
Interesting.
Right.
The same exact thing.
All right. So 8, -3. So now they're going to give me. They're going to take the circle. And they're giving me the spot over 8 down 3. Over 8 down 3. That's a dot. I don't know exactly where that is. I just went kind of right and down, right? Because it's 8, -3. It's positive, negative, right and down. And they want me to find the sine there. And remember, cosine is x, sine is y, right? Cosine is x, sine is y. So they want the sine. There's some kind of angle theta. I don't know if they went to theta like that, or maybe they went that way to get theta. Maybe they went 27 loops around and then went, I don't know. Whatever it is, they ended up at this dot. All I care about in the end is the ending point, huh? So some angle theta, they ended up at the dot over 8 down 3. They want the cosine is always the x-coordinate. The sine is always the y-coordinate. So the sine is the answer, sine of theta, y-coordinate, -3. There's a small problem. I've been saying that up to this point. I've been saying, hey, the cosine's always the x-coordinate, sine's always the y-coordinate. But that's going to be the wrong answer on this one. All of a sudden, I'm changing my tune. Why? Why am I changing? What's different about this circle compared to that other circle we've been using? This is not a unit circle. What does unit mean again? 1. This is not a radius 1 circle. So when I tell you that sine is always the y-coordinate and cosine is always the x-coordinate, I mean on the unit circle. If you're not on the unit circle, if the radius, this r distance, is not 1, then you got to divide by r. That's the real definition. The real definition for sine is y over r. But if r is just 1, you see if you're on the unit circle and r is just 1, then that's just y over 1, it's just y. So that's why I started by telling you the sine is just y. Sure, on the unit circle. on the radius 1 circle. That's true. And cosine is just x. But if you're not on the unit circle, so I'm not on the unit, the 1 circle here, so then sine is y over r and cosine is x over. You got to remember to divide by the radius. Okay, so I got to figure out what the radius is then. I know what the y is. The y is -3, right? So this answer is going to be -3, the y coordinate, right? Here's the x, here's the y, over r. But I don't know what r is. How do I find r? How do I find, looking at this, let me put it back the way it was. Looking at this circle, here's the radius, r. How do I find that? What am I going to do? Over and down. It's over 8, down 3. That's a right triangle. Right? Remember, why is that a right triangle? Because straight over, straight down, that means right angle, doesn't it? Right? Coordinates mean straight over and straight up or down, don't they? So they necessarily make a right angle, don't they? Over 8, down 3. That's a right angle. So this is a right triangle. So our friend, the Pythagorean Theorem, right? A squared plus b squared is c squared. So that would be 8, not cubed, 8 squared plus -3 squared is r squared. Good so far? 64 plus 9 is r squared. 73 is r squared. R is the root of 73. So there we go. Root 73. So the sine is y over r is -3 over the root of 73. Because the radius is root 73. Now I can't leave an answer that way because they don't like roots in the bottom. So you know what to do. Multiply top and bottom by root 73. Get -3 root 73 over plane 73. There we go. Cosine would be x over r. So we'll go, okay, x value 8 over root 73. Can't leave a root in the bottom. Multiply top and bottom by root 73. 8 root 73 over plane 73. There's the cosine. We good? Tangent. Let's do, we got another minute and a half here. What's the, we good to there? Questions so far? Am I racing ahead too quick? You okay? So now, how do we do tangent? Is tangent going to still just be sine over cosine? Yeah, it will. You don't have to worry about the r thing with tangent because it's just sine over cosine. So sine is -3 roots, whoops, 73. I wrote 33. Root 73 over 73 all over cosine, which is 8 root 73 over 73. Right? And then you remember what fractions over fractions? Big old mess. Take it and flip it up. So we get -3 root 73 over 73 times, flip the other one up, 73 over 8 root 73. The root 73's cancel, the plane 73's cancel, and it's -3/8 for tangent. Or we could have just done y over x, huh? Y over x. It's true. Tangent is just y over x. It doesn't matter about the r. You might say, well, yeah, but if sine is y over r now and cosine is x over r, is tangent really just y over x? It is. If you put the r in there, y over r over x over r, the r's are going to cancel. Tangent's still just y over x, so it would have saved a little bit of time. Y over x. And then the other 3 trig functions are just reciprocals, right? Just flip them. All right, we are done there. We didn't finish this section. We didn't mean to, but we did finish 12.5. Binomial Theorem. That's due on Thursday. And we'll keep on with trig for the rest of the way. Test in a week, in 2 days. Have a good day, guys.